Welcome everybody to this, the latest in the series of webinars from the Energy, Environment and Sustainability Group of the IMechE. I'd like to particularly welcome those who are not members of the IMechE, and I think you will find this presentation a very accessible presentation on the current energy scene in the UK and the world. For IMechE members, I've been told to give you a poke in the ribs to vote. There are only 2 days remaining to vote for officers in the IMechE. If you haven't had your email, check your spam. So, energy hierarchy has been a policy from the IMechE for over 10 years now. It was devised as a way to properly prioritize tackling the difficult problem of energy and energy supply. It's been widely and successfully adopted around the world, and in its 10th anniversary, or slightly past it, it was decided that we would do an update to bring it really up to date with how the world is now, as it's very different. And I'm happy to say that it's been published today, and there will be a link available at the end of the webinar. I'd like to present Ian to you, who will be doing the webinar, and he's a senior figure in industry of many years standing, holding positions in many large companies in the energy sector, and in particular sustainable energy. He has run a sustainable engineering consultancy for the last 20 years. He's been chairman of the Energy, Environment and Sustainability Group and a visiting professor at Newcastle, Glasgow and Strathclyde universities. I will be, with no further ado, I'm going to hand you over to Ian, and there will be a Q&A session after Ian's presentation if you have any questions. Over to you, Ian.
Well, many thanks for the introduction. I'll now present this session on the energy hierarchy, a powerful tool for sustainability. My background and experience, which qualifies me to do this, is quite varied. I've spent more than 50 years in manufacturing industry, both in the UK and overseas, and I've had positions from apprentice to managing director in those industries. I've had over 45 years of practical hands-on experience with renewable energy installations worldwide. It's worth noting that that's before we knew it was called renewable energy. More than 20 years as a sustainability practitioner, as both a chartered engineer and a chartered environmentalist, which is sometimes a difficult position to hold, through our own consultancy business, Engineered Solutions, and more than 20 years of teaching and lecturing in renewable energy and sustainability, including teaching a course on energy policies, politics and ethics, an MSc module at Newcastle University from 2006 to 2019 inclusive. And I am or have been a visiting professor in sustainable energy at Newcastle, Glasgow and Strathclyde universities. However, I want to do something rather unusual in one of my presentations. I want to dedicate this presentation to the memory of Sir John Horton, who sadly died of COVID-19 on the 15th of April 2020. Sir John, and some will have heard of him, was a world-renowned climate scientist, indeed former Director General of the UK's Met Office. He was chairman of the Royal Commission on Environmental Pollution, and very significantly, he was chairman of the Scientific Assessment Working Group of the Intergovernmental Panel on Climate Change, the IPCC, second and third assessments. And these have changed the world's understanding of climate change, and virtually all of our legislation in this country and many others is based on the findings of the IPCC. Well, I'm greatly honoured to have worked closely with Sir John and to have had him as a friend and mentor. A great deal of what I am presenting today I learned from him, and I will forever be grateful to him for that. So this webinar is timed to coincide with the publication of an updated version of IMechE's policy statement on the energy hierarchy, which was first published in 2009. That publication argued that the government's sustainable energy goals were unlikely to be achieved by a focus solely on improvements to supply-side technologies, and that a greater focus was necessary on energy demand reduction and energy efficiency. A decade on from that publication, little of this has actually happened, and many goals have not been reached. So the energy hierarchy now needs to be implemented, in our view, so that we can achieve the new 2050 net zero goals. At first, it's worthwhile defining what we mean by sustainability. There are many views out there and many people inventing their own definitions to fit their own particular means. So I want to go back to two of the very earliest. First of all, that from the United Nations Brundtland Report of 1987, which is where it really all started. And it was a very simple statement, that development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Why that's significant is that it shows that we have a responsibility not simply to our own generation, but to the generations to come, to leave the world a sustainable place for our children and grandchildren. And the other definition, which I've personally worked with for the past 20 years, and I really, really like, came from the Engineer of the 21st Century inquiry back in 2000. And it presents it in what, for me as a businessman, is understandable business terms, nothing too technical. So sustainability can best be defined as the capacity for continuance into the long-term future. Sustainability depends upon maintaining and, where possible, increasing our stocks of certain assets so that we manage to live off the income without depleting the capital. Sustainable development is the process by which, over time, we succeed in managing all the different capital flows in our economies on a genuinely sustainable basis. So those are the definitions that we are using in this report and this presentation. The other thing I want to do is define right at the beginning what I mean by energy. And this, I find from years of teaching students, is something that's not clearly understood. Many people in this country, and even engineers sometimes, I'm sad to say, seem to confuse the term energy with the generation of electricity. And it may well be that when you hear the word energy, you may well first think of electricity, even if you don't restrict it to that. But in fact, the use of energy for heating buildings and as vehicle transport fuel is far more significant, both in the UK as a whole and in Scotland in particular. I mentioned Scotland because that's where I happen to live and work, the situation in Scotland is even more severe than it is in the rest of the UK. But it is crucial to any study of energy that we do not create the same confusion. So the second point is that energy does not equal power. Generating plant is often described as so many kilowatts, megawatts, gigawatts, the electrical power rating. But this refers only to the installed capacity, not to how much energy the plant uses or produces. Energy is power used or produced over time and is usually measured in kilowatt hours, which conveniently is our unit of electricity. The electricity that we pay for is in kilowatt hours, or larger plant in megawatt hours, gigawatt hours, or even terawatt hours. And a most important statement, which again never fails to surprise my students, is that energy supply is only required to meet energy demand. Demand must be clearly recognized. And I think it's tremendously important that we understand that from the beginning. So, on the subject of energy demand versus energy supply, despite this last point I made being so crucial, the vast majority of people in my experience, when they think of energy, think first about how it is supplied. In any particular field, they tend to think of their own favorite supply technology, whether that be nuclear or renewable or wave and tidal or whatever. So reaching an ambitious target such as net zero greenhouse gas emissions by 2050, while energy demand continues to increase, will be incredibly difficult if we use only existing supply technologies, perhaps indeed with some minor improvements. We, I believe, will need a game changer, and that, in our view, is likely to be energy demand reduction. The first thing I want to look at as background to this is what I've headed global population and energy demand growth. What we do in the UK is, of course, set in a framework of the whole globe, the planet. The targets that we have for 2050 are not merely UK targets, they are worldwide global targets. And we have to fit in with the rest of the world in achieving those. First graph I want to show you here, I haven't put any text to, I just want you to look at that and see the impression it makes on you. This goes back from about the year zero in the Common Era and projects forward to the end of this century. And you can see for most of that period, up until roughly the start of the Industrial Revolution, that was a fairly flat line at well under 1 billion people on the planet. That was all very easy to manage and presented none of the problems that we have seen over the past 200 years. And as you get to the right-hand side of the graph, you see that rapidly accelerating curve heading up towards where we are now at between 7 and 8 billion people on the planet. We should reach 8 billion by about 2022. And then projecting forward to having something like 11 or 12 billion people on the planet by the end of the century. Numbers, projections differ on that, of course, but there's a general consensus around that. And I think it makes a very vivid visual impact. But to just unpack that a bit more, this is a graph that that dates back to 1992, and it was given to me by Sir John Horton, who I mentioned earlier, as being of primary importance to this whole discussion. And in the inset graph of world population, you can see that in the year 2000, we reached the 6 billion population point. in 2011, we reached the 7 billion population point, and in around 2022-23, we should pass the 8 billion point. And the significance of that is that from those projections in 1992, we're still very, very much on that orange projection curve. So very little has changed in terms of world population. However, when we look at then the other main graph, which is that of world energy demand, you can see that it has continued to grow along that same trajectory into the early 2000s. And then if we take the position with the latest figures we have, which are around 2017, you can see we're still perhaps not on the A scenario curve, but on the B scenario curve, which means that in the course of this century, the energy demand could rise from the 10 gigatons of oil equivalent that we had in 2000 to something like 4 times that amount, 3 to 4 times that amount, of 30 to 40 gigatons of oil equivalent. So it's not just rising on a linear scale. It is rising very, very rapidly indeed. And that has to be taken into account. Now, I'm fully aware that global population is not an easy subject to talk about, or even less easy to do anything about, and I'm not coming up with any solutions to that. I'm merely saying I fail to see how we can continue to just ignore the problem. It is a major, major issue in terms of projecting global energy demand forward, and we have to take it into account. The other thing that we need to look at is the UK's international energy security. And this next graph is taken from the Department of Business, Energy and Industrial Strategies 2019 version of UK Energy in Brief. And it shows the UK's net energy import dependency from 1970 to 2018. And this might come as a bit of a surprise because, contrary to popular belief, the UK is nowhere near self-sufficiency in energy terms and has been a net importer of energy for most of the past half century. Only that period between around 1980 and the early 2000s did you see some net export of energy from the UK, but the whole of the rest of the period we have been importing a very large amount of our energy. And this situation is likely to continue for the foreseeable future. So our ability to import energy to meet our demands is absolutely crucial. And we look closer at UK energy consumption. This is a graph that I drew back in 2009 at the time of the government's renewable energy strategy. I don't have time to spend on this, but it does show that at that time, and it's not so different now, the energy from transport represented about a third of our energy demand. On the right-hand side, electric power, around just over a quarter, and the rest, 40-odd%, is for heat energy. And the green bands at the bottom were showing what, under the renewable energy strategy, we hope to achieve by 2020 in renewable energy terms. And those three added together would give us an overall renewable energy proportion of 15%, and the red dotted line shows you that there. Now, in terms of what will we achieve by the end of this year, the electric power one is pretty good. We'll probably exceed that and have something over 30%. But I have to say, on energy for transport and heat energy, we won't even be close to the targets that we'd hoped. So nor will we achieve the overall legally binding 15%. So that's just by way of background and to clarify the situation on energy demand. This is a chart that we use a great deal in our part of IMechE, the ESG, and it's produced by one of our board members, Dr. Grant Wilson of the University of Birmingham, and I thank him for this latest version. We don't have time to go through this today. I could spend a great deal of time on this, but I'll just explain to you what it shows over the past 10 years. The red line going across the years on a fairly constant basis is our electricity demand. So that hasn't changed much over the 10 years. Above that, you see a stepped line which shows transport fuel demand, and that hasn't changed a lot over those 10 years. The blue line is the one that causes us all the problems, because this is the demand for heat energy. What it actually shows is mostly our consumption of natural gas, but there are other things in there. And you can see that that has declined somewhat over the 10-year period, which is good because it's a major area of energy consumption, as I explained on the last graph. Just as a matter of interest, to show how sensitive these graphs are, if you take the third peak in from the right-hand side, you can see a very large period around March 2018, and that was what we will all remember as the beast from the east, and it does really show up on these graphs. The big problem, of course, with heat energy demand is it is very, very seasonal, and we have very few ways in which we can do that other than the natural gas that we can store for periods of time. Just to finish with this, the green line at the bottom is so-called low carbon energy. That is what we produce from renewables and nuclear. So moving on, this is another graph that is taken from BEIS in their other publication on an annual basis, the Digest of UK Energy Statistics. And it shows energy consumption by sector in terawatt hours per year from 1970 to 2018. And this is quite an interesting graph because it does show a slight decline in overall energy consumption over the past 20 years. And this chart has indeed been used by government to demonstrate that the UK energy consumption has been falling, and that they see this as a desirable outcome. So obviously energy demand reduction is seen as a good thing by government. However, the problem I have with this graph is that this disguises the fact that transport energy consumption, that's the blue bit on the graph, has risen dramatically over that period, and that the huge reduction in industrial energy usage, that's the red bit on the graph, over that same period is simply explained away as deindustrialization. So this benign-sounding deindustrialization, supposedly reducing UK industrial energy demand from about 43% of the total to just 17% of the total, is perhaps better explained by the offshoring of much of the UK's former manufacturing sector to developing countries, along with all of the related energy demand, costs, and greenhouse gas emissions. This was demonstrated in a recent Office for National Statistics report showing Britain to be the biggest net importer of CO2 emissions in the G7. We continue to consume the product, but we don't account for the emissions in making that product. So the UK benefits from lower cost of production, but expects other countries to account for all of the associated greenhouse gas emissions. That does not seem right. Furthermore, the huge increase in transport energy consumption since 1970 still does not include either international aviation or shipping, each of which sectors is now responsible for approximately 2% of all global greenhouse gas emissions. So coming now to the energy hierarchy, as I mentioned before, the concept of an energy hierarchy was firstly developed within the institution of mechanical engineers in the early 2000s. And it was publicly launched at the International Congress of Mechanical Engineering Societies in Brussels in 2007. And following widespread endorsement from other international engineering institutions around the world, it was eventually published as an IMechE policy statement in 2009. So this is not new. This has been the institution's policy for the past decade or more, and it's perhaps a pity that it's not better known. The concept of the energy hierarchy is simple, and it's shown in the chart on the left-hand side, which is taken from the new publication. And it goes from tier 1 at the top, energy demand reduction, through tier 2, energy efficiency, tier 3, utilization of renewable sustainable resources, tier 4, utilization of other low greenhouse gas emitting resources, and tier 5, utilization of conventional resources as we do now. And this takes us from the least sustainable at the bottom, what we do now, to the most sustainable at the top, what we should aspire to do. The energy hierarchy follows the rule that a kilowatt saved is more valuable and more sustainable indeed than a kilowatt produced, no matter by what means. Similarly, the higher up the hierarchy we go, the more sustainable the process becomes. So how the energy hierarchy works. Tier 1, as I've explained, energy demand reduction, and that simply means do not use as much energy. Tier 2, energy efficiency. That means find more efficient ways of supplying and using energy. Tier 3, renewable, sustainable energy resources. Those are the ones with the least environmental impact. Tier 4, other low greenhouse gas emitting energy resources. So these are the technologies that will reduce the amount of greenhouse gases that we put into the atmosphere. And tier 5, conventional energy resources the way we currently do it. So the first tier of the hierarchy, which is energy demand reduction, is a demand side measure which often requires lifestyle change, and I think that's the important thing, but has the greatest, quickest impact on demand reduction and greenhouse gas emissions. It should be obvious that a greater impact can be made by saving a kilowatt of energy than finding a better, cleaner way of producing a kilowatt of energy. There is no efficiency factor, for example. This concept, by the way, is also known in some terms as the negawatt, which is an interesting expression. Examples of this are using all forms of motorized transport less, insulating buildings better, passive solar and low emissions building design, turning thermostats down, holding virtual meetings and conferences, etc. It's interesting to note that we wrote all of this before COVID-19, the COVID-19 crisis, But before that, this was considered almost impossible to achieve in a developed society such as the UK. Yet now we can all see the benefits, particularly environmental, that have ensued from this energy demand reduction. It's staring us in the face. The second tier, energy efficiency, is both a demand and a supply side issue. On the demand side, this requires the use of low energy appliances and lighting, highly efficient space heating devices, micro CHP, hybrid and low fuel consumption vehicles. On the supply side, this involves making much better use of energy input to energy output ratios, such as CHP, district heating schemes supplied by electricity generating plant. Engineers must play the primary role in achieving this, but energy efficiency has to be promoted and rewarded by government, and it really isn't so far. Care must also be exercised to avoid what's called Jevons paradox, which dates from the 19th century, when they found that increasing energy efficiency may simply lead to greater energy consumption, which would be defeating the objective. The third tier, renewable sustainable energy, is a supply-side measure involving the use of fuels which have the lowest overall, this is on a whole life cycle evaluation, environmental impact, and which meet the other sustainability criteria, both economic and societal. Almost all renewable forms of energy can also be considered to be sustainable, although care must be exercised, for example, with large-scale hydroelectric schemes. Biomass and other biofuels are also important renewable fuels, but require very careful whole life cycle analysis to ensure sustainability. Our engineers will continue to lead development in this tier, but care must be taken to ensure the achievement of the first two tiers is prioritized so that the targets to be achieved are not continually growing. The fourth tier, using other low greenhouse gas emitting energy resources, is another supply side measure which includes other energy supply technologies which achieve reductions in overall life cycle greenhouse gas emissions. This can include thermal power generation from cleaner hydrocarbons, for instance, or nuclear, although these have other environmental and societal issues which have to be addressed in the sustainability analysis. Although the current UK practice of gratuitously wasting the co-generated heat energy from thermal power plants must cease. Lower carbon content vehicle fuels will also significantly cut down greenhouse gases, but may well have other sustainability issues. Hydrogen, very popular at the moment as an idea and as an energy vector, may also be included here, although it also has significant sustainability issues which will have to be addressed. You get nothing for nothing. So if the first four tiers can be successfully implemented, then it follows that the fifth tier, that is doing what we currently still do, but perhaps a little bit better, need never take place, and existing forms of power generation, space heating of buildings, and fueling of motor vehicles can eventually be phased out. This also means that continued exploitation of finite reserves, especially fossil fuels, will decline and will become much less of a strategic issue. So the conclusions and recommendations, and these are the conclusions and recommendations from the report I want to share with you. They say this: if the 2050 net zero greenhouse gas emissions targets are to be met, the UK's present energy policy remains inadequate, and the Institution of Mechanical Engineers believe that the UK's energy policy should, 1, be redeveloped with the energy hierarchy as its framework, in keeping with the principles of sustainable development. Policy will need to be targeted much more at demand-side energy conservation and efficiency measures, alongside the more rapid development of a wide range of renewable and low greenhouse gas emitting energy sources for heat and transport, not just for electricity. Recommendation 2, include a statutory national target on energy demand reduction which will achieve genuine reductions, not those achieved by industry outsourcing its own emissions problems to developing countries while reaping the benefit from lower cost of production. And thirdly, urgently provide a long-term framework giving investment signals for businesses to develop major energy system change. This must go well beyond the current economic and technical assessments and enable the private sector to make real business cases which can avoid the boom and bust created by the feed-in tariff and to some extent the renewable heat incentive. For example, any economic case analysis, and an economic case is quite different from a business case, but an economic case analysis must also fully consider all external factors, not just a few. So those are the recommendations. And I just want to conclude with what I'm calling a way forward for net zero. For the past 200 years or so, that is the aftermath of the Industrial Revolution, the UK, along with many other countries, has had a policy of trying to reach strategic energy objectives by focusing almost exclusively on supply-side technologies. Unlike most other Northern European countries, little thought has ever been given to reducing energy demand to make energy supply objectives more readily achievable. Since 1990, when the first IPCC assessment started to make us all aware of the need to mitigate and or adapt to climate change, the UK's energy goals and targets have become increasingly more based on sustainability goals. Despite this, the proposed methodology of achieving these goals has remained firmly with a greener, cleaner supply side. Making efforts to reduce energy demand has not met with any great success so far. Consequently, the 10% renewable electricity by 2010 target was not achieved. The 10% renewable transport energy and 12% renewable heat energy by 2020 targets, as we've already seen, will also be badly missed. Yet despite this poor track record, virtually all of the measures that are being proposed to achieve the 2050 net zero greenhouse gas emissions target are also supply-side technologies with only slight improvements over what has gone before. This does not augur well. To paraphrase G.K. Chesterton, it is not that energy demand reduction has been tried and found wanting. It has been found difficult and left untried. This is because a prerequisite of energy demand reduction is human behavior change. Unless each of us changes the way we live, we will go on trying to consume more and more energy. In many years of lecturing on this subject, I've been fairly consistently told that human behavior change is just too difficult for people in the developed world to embrace. However, the present COVID-19 crisis has changed all of that. Behavior change has been forced upon us, and the results have been amazing. We might not like the experience, but the results are very clear. Energy consumption in the UK is down to levels not seen since the 1960s. Globally, climate scientists are already saying that 2020 will see the lowest recorded greenhouse gas emissions in decades. So, if nothing else positive comes out of this terrible pandemic, let us make sure that the new normal, as it's called, after the crisis is over, does not simply revert to our old energy wasteful ways. Following the principles of the energy hierarchy will help us to ensure that our world will indeed be a cleaner and greener place for our children and our grandchildren. The following quotation, taken from Rachel Carson's Silent Spring of 1962, she was probably the first notable environmentalist. She said this: "Humankind is challenged as it has never been challenged before to prove its maturity and its mastery, not of nature, but of itself." And if we are serious about achieving the goal of net zero greenhouse gas emissions by 2050, it will require behavior change. We cannot rely solely on supply-side technologies. The principles of the energy hierarchy are strongly commended to you. Many thanks for listening, and I'm sure there will be questions.
Thank you very much indeed, Ian. That was very interesting. I'd like now to invite people to put questions into the Q&A box. We've already got quite a large number, so I'm going to apologize in advance for not being able to answer all of them. But we'll start, if we can, with the first one. So the first one basically says, could you please repeat the important statement you made at the beginning of the webinar, where you compared the difference between energy production and energy as a whole?
I'm not quite sure that I understand the question. I don't think I made that particular statement. I was distinguishing between energy demand and energy supply. Supply, of course, is production, but the presentation was very much focused on what we can do to reduce energy demand and improve energy efficiency. And of course, we also need to improve energy supply. But those are the things that we are already focused on. And I was emphasizing the ones that we are not currently very much focused on.
Thank you very much. Second question. I was particularly struck by your statement that a kilowatt hour saved is more valuable than a kilowatt hour produced by whatever means. I presume this means more sustainable too. Can you explain this assertion, please?
Yes, it's principally a matter of efficiency. A kilowatt saved is 100% efficient. You get the full value of the kilowatt. No matter how you supply the kilowatt, there will be an efficiency factor, and so we have to accept that in primary energy terms, the kilowatt supplied from, say, a generating plant is a tiny fraction of the full kilowatt in primary energy terms. So the difference is very large indeed in most cases, and that's really the point I was trying to make.
Thank you very much. I've noticed a lot of questions come in asking where we can get the report from. It's on the IMechE website under news, and all of the people who have registered for this webinar will have it sent to them after the webinar. So if you want to look at it straight away, hop on the IMechE's website. Otherwise, you will get it in due course. Next question is how do we go about systematically looking for opportunities to reduce energy demand, seeing as many of these cases, like poor insulation, are side effects of some other use case?
Yeah, well, that is, of course, the very hard question, because it's not easy to systematically go about it, because we all know that we live in buildings, or we use buildings that are in this country that are hopelessly insulated by and large, and that we waste an awful lot of the energy that we consume. But what we're trying to present in the report is the idea of whatever energy project you're looking at, whether it's supply side or demand side doesn't matter. What you should always do is conduct a sustainability analysis and look at how sustainable that process is based on the definitions of sustainability that I gave at the start of the presentation. But then look to see where significant improvements can be made. And certainly, until we change and implement legislation in this country, we're never going to get the results that are commonplace in, say, Scandinavian countries. But we have to start moving in that direction, no matter how difficult a task it is.
Thank you very much. The next question is, what is your view on the conversion of DRAX to biomass? Do you see it as sustainable, including the transport of feedstock from North America? Do you think it's right to call an operation of that scale renewable?
Well, very good question. And I must admit to some previous here. I've worked in the biomass sector since 1974, so I know the biomass CHP industry very, very well. I've been to DRAX, and it's a hugely impressive operation. I think there's very much commendable about the conversion of DRAX to biomass firing. To be picky on words, because it's biomass, it is absolutely renewable. There's no question about that. So the question is it sustainable? And I don't want to make a definitive statement on that, but the questioner is absolutely right, that it's bringing the wood chip from a very long distance, and again I come back to the point that you'd have to make, that you have to do a full life cycle sustainability analysis of the entire process, and that's much too big a task to cover in a short answer, but that's what needs to be done. I would also add that to me, it's very difficult to call a process sustainable where you continue to waste the co-generated heat in the power plant to either water courses or atmosphere, and that's a point we do make in the policy statement.
Thank you very much. The next question is, great presentation and fascinating, thank you. Most of the statistics used by UK governments and agencies and internationally use greenhouse gas emissions as the measure. Up to this point in the presentation, you have shown a preference for taking gigawatt hours of energy as a measure. Please give pros and cons.
So I didn't entirely follow that. The distinguishing gigawatt hours from
using as a measure as opposed to greenhouse gas emissions.
Well, yes, gigawatt hours are a measure of energy, and this is the energy hierarchy. So that's why I use the gigawatt hours in the presentation. Greenhouse gases are not. They're certainly linked to energy production, but the greenhouse gases emitted from different types of energy production are different. So you would need to look at each process in its own right to see what the greenhouse gas emissions from that were. And again, I stress the point that you have to look at greenhouse gas emissions not just at, say, a power station, but in all of the upstream and downstream processes related to that energy production. In the case of oil and gas, for instance, right from the extraction from the well all the way down to the electricity used in the appliance in the home, for example. That's what we mean by whole life cycle analysis. That doesn't really lend itself to being measured in gigawatt hours, but it is a very important analysis to do.
Thank you very much. Next question is, how much evidence have you seen of projects working within these recommendations already? Does that mean that legislation is the only way forward?
Sorry, does it mean that what is the only way forward?
Legislation.
Yeah. Legislation is a very difficult area because we've had lots of legislation over the years, and then we've had legislation changed. I gave a couple of illustrations of in the presentation of feed-in tariff and renewable heat incentive, both of which were very well intentioned, both of which ran into fairly bad problems and were strictly curtailed. So legislation is absolutely vital, but it's getting legislation right in the first place so that we don't have the kind of constant level of change that we've had in this country over the past 30 years. And this is in sharp contrast, say, to other Northern European countries where there's far, far greater consensus in government in terms of energy policy. Denmark, for instance, which is the greatest exemplar in many respects, all of the political parties are completely aligned on energy policy, however much they might differ on other things. So that makes it an awful lot easier to legislate for energy policy.
Thank you very much. In levels 3 and 4 in the hierarchy, there are many options whose sustainability are quite nuanced and context specific. So agreed life cycle analysis is needed, but this allows ambiguity to creep in and technologies like waste incineration to be advanced as arguably more renewable than they really are. Is it not worth having some kind of sub-hierarchy within these two sections to guide policy more wisely?
That's a fair comment. You have to remember this is a very high-level overview of the situation, and the intention of the institution is that within each of these areas there will be further publications and consideration given to specific processes. We've not tried to do that in a high-level overview. Of course, people's opinions differ. I would object to, for instance, the use of the word waste incineration when the last municipal waste incinerator in the UK closed in 1993. We need to look at what's actually happening now and do an analysis of what is actually the case, not what our preconceived ideas might think is the case. The sustainability analysis will bring all of that out.
Thank you very much. So we have your assertion about population versus energy demand is somewhat simplistic, as the demand is not uniform and the Western world has a far higher per capita demand than the developing world. So it is much more important that energy demand is stemmed in most energy-intensive nations rather than pointing the finger at large populations in developing countries. It's a statement rather than a question, but I'm interested in your comments.
Well, yes, it certainly was a statement, but yeah, I wasn't setting out to make a value judgment there, and I was in any case using other people's numbers, not mine, merely commenting on them. It is, of course, true that we use much more energy, much more wastefully in the developed world than is the case in the developing world. And I think there's a very good case to be made for allowing the developing world to use more energy, and certainly the focus needs to be on the developed world and what we can do to reduce energy. But what we must not do is allow the developing world to simply go on doing the bad things we did. That really is not going to take us forward at all.
Thank you. We're coming towards the end, but a couple more questions. What energy gain opportunities exist in food production? Do you believe that the food we eat today will remain similar, or are there any possible big changes?
Well, yes, that's a very, very big question. And a few years ago, the Institution of Mechanical Engineers produced an excellent report on food waste not, want not, and I'd refer the questioner to that. The problem with food is that it is such a huge subject in itself that it's very hard to make a short, simple answer to it. I think there seems to be general consensus that just in order to feed the world's population, there is going to be a move over the next few years away from meat eating to a more vegetarian diet. But that in itself is fraught with difficulties, and I think is way beyond the scope of this.
Okay. What do you think would be the outlook from this energy hierarchy, at least in the UK itself? Do you think the government would be compelled to fully implement this? Also, do you think the hierarchy is universally implementable in the rest of the world, including third world countries?
Well, to the last point, yes, I do. I think it is universally applicable. I've had the privilege over the years of doing business in more than 70 countries around the world, so I have a lot of direct experience of the developing world, and I do think it's implementable. Whether government will buy into it, who knows? Government has many things to consider, not least the large vested interests who pay a lot of money into the exchequers. So that's a question that's way beyond my ability to answer, I'm afraid.
Okay. This speaks to your Jevons paradox, where, but it says, what would you advise government to do to avoid the rebound effect from energy efficiency reduction measures, creating additional demand, therefore negating the effects of the reduction? Is this why government focus? Is this why government focus is on supply side solutions?
Yes, I think that is the case. It is very hard to legislate on demand side reduction and energy efficiency, but that's why I believe, and perhaps that's where we need to finish. The message of the energy hierarchy is behaviour change. And that means behaviour change for everyone. That means behaviour change in government. It means behaviour change in large organisations. It means behaviour change in small companies. It means behaviour change by individuals. Unless we all pull together on this, I don't see any real chance of any of the current policies getting us to where we need to be.
Well, thank you very much, Ian. I think we need to draw this to a close. It's been very interesting. Thank you for everybody for the questions, and apologies to all those who haven't had their questions answered. But I hope we've covered the general drift of them. Just to reiterate, the report is available in the news section of the IMechE website. That's IMechE.org. So do please go and visit that if you would like it immediately. Anyone registered for this will have also get this sent to them after the event, as well in a few days' time, a link so that you can review the presentation. So I'd like to thank Ian and the team that are supporting us to produce this webinar, and wish you all a good afternoon.
Thank you.